In this video, we're going to talk about the area of a region between two curves. So the idea behind this concept is that it's exactly what it sounds like. It's the area between two different curves. So what we've already looked at is the area underneath one curve, and as it's bounded by two values, usually to the x-axis, right? So some x equals a to x equals b value, and that applies to the y-axis as well. But we've only looked at one curve. So for example, if I had this curve f here, I could find the area under that curve between the x-axis bounded by x equals a and x equals b. Easy enough to do. But what's cool about calculus is that, let's say I have two curves. So let's say I have this f curve, and I have another curve here, let's call it g, and I wanted to know the area between those two, between those same x values, so a and b. What you would do is you would integrate between those two x values or y values, and you would take what I like to call the bottom function, so whichever one is beneath the top one. So in this case, g is beneath f in this case. So you would take the integral between a and b of f of x, the top one, minus g of x, the bottom one, of d of x. So let's try out a few examples. Let's find the area of the region bounded by the graphs of x squared plus 2 and y equals negative x from x equals 0 to x equals 1. So we have it modeled here, and I always suggest that when you're first starting out with these problems that you actually graph the two functions so you can figure out which one's the quote-unquote f of x, the taller one, and which one's the quote-unquote g of x, the shorter one, if you want to call it that. So in this case, I know that the top one, or my f of x, is going to be the x squared plus 2, because from 0 to 1, that one right here, the x squared plus 2, is taller than the y equals negative x. So I'm going to take this idea and plug in what I have and see what I get. First thing I do here is I, again, just identify which one's my f of x, my taller function, and which one's my g of x, my bottom function, or my shorter one, and I just plug it into this model here. Now I know a is 0 and b is 1 because it goes from 0 to 1, and really all I need to do is simplify this and integrate and plug in my 1 and 0, and I could find the area between those two curves. So I combine these two functions and I get x squared plus x plus 2. When I integrate, that becomes 1/3 x cubed plus 1/2 x squared plus 2x. From 1 to 0, I plug in 1, plug in 0. I make a common denominator here just to add them up, and obviously that becomes 0. So the area between these two curves from x equals 0 to x equals 1 is 17/6. So now let's take an example where we have an area of a region between two intersecting curves. So we want to know the area between two functions. One is f of x is equal to 2 minus x squared, so that is this negative quadratic right there, and g of x is equal to x. So we see that the quote-unquote top function is f of x because it is above g of x right there, but it doesn't give me any bounds. I can find them either graphically, or I can set these two equations equal to each other and find what those a and b values will be. And what that looks like is 2 minus x squared equal to x. I move over these two items and I have a quadratic set equal to 0. I factor and I find my a value to be negative 2 and my b value to be 1. So I place those here and I have my area equation. Going to integrate, plug those in, and then find my area. So when I combine these functions, I get negative x squared minus x plus 2. I just reordered it to put the highest power in front. So this is my function when I integrate. I plug in 1 and then negative 2. I subtract those values from one another. I saved some room here by skipping a little bit of the arithmetic, but this is what we get when we consolidate when we plug in 1. This is what we get when we consolidate when we plug in negative 2. And all of that works out to be a simplified fraction of 9/2, or 4.5. So that is the total area between those two intersecting graphs. So here's another example that's kind of interesting in my opinion. So we have here the sine and cosine curves, and now they're going to intersect infinitely many times over the entire domain of the x-axis. But bounding regions of equal areas between, so like this guy right here is equal to that area right here. So we just need to find the area of one of those regions. Now, the one that's highlighted from the book is the one that we're going to pick, but honestly, you could have picked this one or any other overlapping region because they told you the areas are going to be the same. So it's going to depend which area you pick, obviously, because if we look here, the sine function is the top one, but on this one, the cosine function is the top one. So you just have to be careful of that, but you should get the same answer. So I don't have intersecting points given to me. So just like the last example, we're going to set sine and cosine equal to each other and see if we can't find two values that will allow us to find an a and b. So when I go to look for those a and b values, I'm going to set sine equal to cosine, and I'm going to consider the full unit circle, or the from 0 to 2 pi, essentially. And I'm looking for two values because I need an a and a b, and I know two places on the unit circle where sine and cosine give the same value for the same angle. One is pi over 4, or 45 degrees, because sine and cosine are both positive rad 2 over 2 at pi over 4. And the other one is in the third quadrant at 5 pi over 4 because they're both negative square root of 2 over 2 at that angle. So A is going to be pi over 4 and B is going to be 5 pi over 4. And my f of x is sine because from pi over 4 to 5 pi over 4, sine is the top function. And then I'm going to subtract cosine because it's the bottom function. So let's work this out. So I integrate sine minus cosine, and I get negative cosine minus sine, and I have a little bit more room here, so I can show you what happens when I plug in 5 pi over 4, and that becomes negative rad 2 over 2 for both sine and cosine here, and for pi over 4, that becomes positive rad 2 over 2. So when you combine these things, you get a square root of 2 here, plus another square root of 2 here, so the area between any of these intersecting curves is going to be 2 square root of 2. Now, the next question you might ask is, well, what about curves that intersect at more than 2 points? Well, I'm glad that you asked that question. And even if you weren't wondering, we should probably figure out how to do that. So let's say I have these two functions. I've got a cubic here, so 3x cubed minus x squared minus 10x, and I have a negative quadratic of negative x squared plus 2x. So if you graph this, you'll see that on the left-hand side over here, that f of x is actually the top function here, but once you pass x equals 0, or the origin, it becomes the bottom function here. So how do we deal with the area of essentially two pieces? Well, the first thing that we're going to want to do is we're going to find all the intersection points, so that way we can figure out what our a and b values are going to be. And then we're actually going to find the area of this curve, or that area between those two curves, separate from the area here, and we're just going to put them together. So when I set f of x equal to g of x, I have my function here. I'm going to move over g of x here, and I get a nice function that I can pull a 3x out of. So 3x equal to 0 gives me x equals 0, so that's one of the intersecting points. And I see that x squared minus 4 equal to 0 is x plus 2, x minus 2 when I factor it. So I know that negative 2 and positive 2 are the other two intersecting points. So it makes sense that I get 3 answers here, because there are 3 intersecting points. So I can confirm that graphically as well, if you prefer to do it that way. And so I've just decided to take the leftmost region first to find the area under that two sets of curves. So I noticed that negative 2 is going to be my a value because that's the leftmost point, and 0 is going to be my b value here. And so the top function, my f of x, is actually f of x, so it's this function here. And then I will subtract g of x from that function, because this guy right here is the top, and that guy, or g of x, is the bottom. So let's put these together and figure out what the area underneath that curve is. So when I subtract this function from this one, I get 3x cubed minus 12x, and here is the integral of that. That becomes 3/4 x to the 4th minus 6x squared, because that 12 and 2 becomes 6. I'm going to plug in 0. That gives me 0 for everything. And then when I plug in negative 2, I get 12 minus 24, and that negative is still hanging out on the outside, so that becomes negative 12, which is 12. So that's not the answer to the whole thing. That's just the area of this part right here. So we're going to take that area that we have, so that is 12 over here. We will add it to whatever the area we get for that second portion. So the solutions that I found for when I set those two equations equal to each other, I have 3 intersecting points, remember? So we took care of -2. We're not going to need that in our second area here. We're just going to need the 0 and 2. So 0 becomes my A because that's the leftmost point, and +2 becomes my B because that's the rightmost point. But notice that my g of x is my top function here, so that's the function that goes first. And then I'll subtract the bottom function from it, which is the cubic. So let's work this out and figure out what that area is and add 12 to it and be done with the problem. So when I combine these two functions, I get -3x cubed plus 12x. I integrate, looks very similar to the last function, so that makes plugging in the same kind of numbers kind of nice. So I get a -12 plus 24 here, minus 0, because when I plug in 0, it zeroes everything out. So that I get a +12. So actually this area and that area are the same. So 12 plus 12 makes the total area between these two intersecting curves to be 24. And the last example I want to work through is something that is considered to have horizontal representative rectangles, which just means that it's two equations that are not in terms of x, they are in terms of y. So normally if I did these individually, they'd be bounded by the y-axis. So that doesn't change the math that we're going to do. We just want to take any integrals in respect to y instead of x. So we have two curves here, x equals 3 minus y squared, and x equals y plus 1. Now, I don't have a graph here, so let's try to do this all algebraically. Now we don't have any y values to restrict this to, so we're going to have to set them equal to each other and figure out what those intersecting values are going to be. So I set 3 minus y squared equal to y plus 1, I move things over and I get a positive quadratic, I factor, and I find -2 and 1 to be my a and b values respectively. So I'm going to cheat a little bit and I'm going to graph these two functions. Now, normally I talk about, okay, which function is higher than the other, but when you're dealing with functions that are in terms of y and not x, so something like quote-unquote bounded by the y-axis, if you like to think of it that way, I have to figure, all right, if I were to flip this graph on its other axis, so it looked like the x-axis. Really, I'm looking for, okay, the function that goes first is the rightmost function. So if you turn your head 90 degrees to the right, this function right here would be your topmost function, so, or the rightmost. Hopefully that makes sense. So my rightmost function is my g of y right here, so my 3 minus y squared. So that's why that one goes first. So I'm going to subtract y plus 1 from that and integrate between 1 and -2 and see what that area is. So when I put these two functions together and reorder them in order of power, I get -y squared minus y plus 2. Please notice that dy is next to it because it's in respect to y, not dx. So this is the integral I get. When I plug in 1, I end up with 7/6, and when I plug in -2, I end up with -10/3. Put those together and simplify it down, you get 9/2. So that's the area between those two curves. And one quick note about this last problem before I leave you is that you can totally actually integrate this kind of function in respect to x, but you will need multiple integrals to do that. So you would need to rewrite these functions in terms of y equals something in terms of x. You'll have some more integrals to contend with and some more points to figure out. You'll still get 9/2, but why? When you can do it in respect to y and do it much quicker. That's all. All right, that's going to do it for this video. Thanks for watching.